Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA Compute Memory and Storage presentation. Today's presentation is on composable infrastructure and computational storage. Before we start, I'd just like to tell you a little about the interface. In front of you, you've got an image of the screen. Some of the slides do have fairly dense diagrams, and if you're finding trouble in seeing them in all their detail, then you can enlarge the screen itself to your full monitor size, and that may help you identify smaller features of some of the graphics that we've used today. Secondly, you'll also get, on the way out of this presentation, the ability to give us some feedback, and we'd love to hear what you think about these presentations. The feedback rating is from 1 to 5. 5 is, love it, give us more, and 1 is, I think I should have been doing something else. And certainly a comment or two would help us as well if you've got any observations that you'd like to make. And last but not least, we will make sure at the end of this presentation that you have the ability to download the presentation from the website, and I'll be showing you at the end of the presentation the links where you'll be able to get this information. In the meanwhile, just let me move forward one slide, and I'm going to introduce the speakers for today. I'm your chair, I'm Alex McDonald, and I'm the co-chair of the SNIA, complicatedly named Compute Memory and Storage Initiative, but you can probably work out what we spend most of our time doing. That's talking about compute memory and storage, would you believe. Today's main presenters, though, two of them, we have Philip Kufeldt, who is from Seagate Technology, and is a member of the SNIA Computational Storage Technical Work Group, and Tiomkin, who is from NGD Systems and is also from the Computational Storage Special Interest Group. They're the people that market what the technical work group do. So without further ado, let me move again forward and tell you that this presentation is a work in progress by SNIA. Basically, the copyright belongs to us, and thanks for observing the copyright. You're obviously free to make extracts for the purposes of commentary. But remember, there are no warranties with this, express or implied, and you use it at your own risk. None of us is a lawyer, but that basically means if whatever you brush up against this presentation, if it breaks into 2 bits, both of those bits are yours, not ours. SNIA itself is an organization, the Storage Networking Industry Association, for the promotion of storage and networking. And we've got about 185 industry-leading organizations, some of whom are here today to talk to you, about 2,000 active contributing members in terms of technical work groups and various other initiatives, and around about 50,000 IT end users and storage pros worldwide, of whom you are part of this large community that we regularly address with technical topics. So today's presentation, just to remind you, is about composable infrastructures and about computational storage. So we're going to talk a little bit about the need for change in the way that we address storage and look at storage, and also other elements of our overall IT infrastructure, whether it be at the edge, in the center, in the data center, the way that we treat things like compute, networking, memory, and storage. And we're going to talk a little about that, and Philip's going to take us through composable infrastructure. Then we're going to talk about a new class of storage, computational storage. That's storage where we're actually doing more than just storing the data and allowing you to retrieve it. We can do all sorts of clever and interesting things with the data while it's down on the devices. And then we'll take a look at whether these 2 ways of looking at our infrastructure are mutually exclusive, i.e. do you do one or the other, or mutually beneficial. So without further ado, I'm going to invite Philip Kufeldt to take us and talk to us about computational infrastructure. Thank you, Philip.
Thank you, Alex. I appreciate it. So before I start, when Eli and I were asked to do this presentation, the fundamental question was about composable infrastructure and computational storage and whether or not they're mutually exclusive or beneficial. And so to answer that fundamental question, which is the last agenda item, we said that we would, essentially go through what is composable infrastructure and what is composable computational storage, kind of motivate them from, why we need these two things, what is the problem that they're solving, and then how do they solve it. But to cover all that kind of material, composable infrastructure for itself is an entire presentation unto itself, as is computational storage. So the presentation is needfully, not too deep. So we don't really get into, sort of the technical specifics of how these things are accomplished, but more about, what, from an overview point of view, what do these solutions look like and why do they exist? So I start off with talking about a need for a change. And this is primarily focused around the composable infrastructure and can be applied to computational storage as well. We have seen, over the past decade, we have moved, from virtualization technologies to run our applications that interact with our clients and our customers. We've moved from virtualization to container infrastructure, and both of these things have one thing in common, that they're essentially allowing us to encapsulate essentially an app into some sort of vehicle that we can easily manipulate. We can schedule it on different physical servers, and we can start it and stop it and move it and scale it. We can produce multiple copies of these things, but all of these things are around, how do we faster respond to new applications coming online, as well as the elasticity needs of applications. Similarly, we've had to do the same thing in storage, where we've created composable infrastructures for storage such that we can easily create new volumes for these applications to use as their persistent stores. But we're now starting to see that we're running up against, flexibility even today, even with these great, container environments that we have today. And so we're moving more towards a composable infrastructure. And I'd like to motivate, really why do we need to take another step? And I start with talking about the application itself, right? In the cloud environment today, we interact with our clients and customers through applications. We provide, music services and web services and database services and tons of services out to our clients. And these applications have been growing exponentially for the last several decades. Every day we add new services that we provide to people. Every day we modify those services, we improve what they can do. We're very agile about how we evolve and fix problems and then deploy these applications. But fundamentally at its core, we have these applications that need hardware to run on, and they all have requirements associated with them. So as we write an application, we essentially build into that application architecture exactly, how many CPU cores do we need for this particular application, or how much memory does it need? Interaction with our clients through the network requires bandwidth, and maybe even locality due to caching and latency requirements. There are availability requirements for that application. And then when it's time to store the data that the application needs to read and write, we have a plethora of choices we have to make with regard to bandwidth. Can it use slower media like HDDs, or does it need faster access times and lower latency that an SSD provides? And then there's capacity concerns. How big is the data set that application is actually accessing? So all of these things kind of form the requirements of a given application, and just some examples of these are database services or web services or machine learning applications. But I think the fundamental takeaway here is that every application has a set of hardware requirements that have to be mapped onto physical hardware, and that the sheer numbers of applications, the requirements are constantly growing at pretty much an exponential rate. And that's been historically fine, that we have been growing our number of applications and their requirements on the underlying hardware, because we've had this great thing called Moore's Law that has allowed us to functionally double the capability of a platform every 18 months. So we have been functionally geometrically increasing the capabilities of our servers. At the same time, our demands have been geometrically increasing at the same time. But unfortunately, in the last decade, we've started to see some problems with that. We've started to see some of those fundamental laws that we've depended on for so long starting to come to a close. I think we first started to see Dennard scaling, and even 10 years ago, where power leakage and heat started to prevent us from increasing the scaling of our processors. Right? We've been kind of stuck at sort of a 3 gigahertz level for almost a decade now, and that doesn't seem to be changing. So we can't make them faster. An individual core processor, we really can't make it faster by increasing the cycles. And so we compensated for that by starting to add many cores to a particular processor, so that we had more units. They're all operating at the same speed, but we had more units to utilize. But then you start to hit restrictions around Amdahl's law that applications can only be parallelized so far, not paralyzed, but parallelized so far. And such point that multiple cores don't really help you because you can't leverage them. And then finally, Moore's law itself, the ability to shrink the size of the transistor and pack more and more capabilities into a single processor is really starting to tailor off. And so we've reacted to that over the last decade by starting to create what's called domain-specific architectures, right, where we have processors that are dedicated to particular tasks. We've all seen, GPUs have been around forever. We're now seeing them being leveraged as accelerators for machine learning and other specific computational tasks. We've also seen the addition of offloading network interface adapters, where we can offload the TCP stack completely, or maybe we just offload some of the processing of the stack itself off of the main CPU and onto the device itself. Google introduced in the last 5 years a device called a tensor processing unit, which is really focused around machine learning and accelerating AI and machine learning in hardware specifically. And in the last 5 years, we began to see FPGAs being deployed as accelerators in the storage space, where FPGAs could accelerate databases through accelerating either compression or encryption, or even possibly doing some offloading of searches in hardware between the storage and the actual processor itself. And these are all great, and they are allowing us to continue this rapid growth of applications. But now we're starting to see that's increasing the complexity of the hardware that we have to build to support all these applications. So what does an application look like, today? Is that now, instead of just deciding on what processor I need and what cycle speed I need, I now have a choice. I can decide that I can use a CPU, or maybe I want to use an SoC for this application. The number of cores, I can decide, anywhere from, a multi-core processor, 2 cores up to, 48 or even higher number of core counts. DDR capacity for an application and in the server, is very wide and varied. We see servers that range from 64 gigabytes up to terabytes of memory, depending upon the application requirements again. We have many choices with regard to NICs and accelerators inside the system. And this is also true in the storage world. We have seen a proliferation of, specific storage options that allow you to tailor, what kind of throughput requirements you have, what kind of latency requirements you have. So it could be that I use cold storage, which is a high latency type of storage device, to persistent memory, which is a very low latency, almost like main memory type of latency storage device. And all of these things are now being built into our applications as fundamental requirements of the hardware itself. And this means that I have to figure out when I build a server, based on my application requirements, what kind of server I'm going to build. And frankly, you can't just build one. You end up having to build classes of hardware for all of your application load to run on. So that's really where we start to see what the problem is in the composable infrastructure world, and why composable infrastructure is interesting, is that application requirements, as I've discussed, are very wide and varied. They require complicated sets of hardware requirements. With our agile world, our applications are evolving at a very rapid pace. Every sprint, if you're familiar with agile process methods, generates a new version of that application, and across every version, the requirements can evolve. I can increase the amount of CPU I need. I can increase the amount of memory that I need because of the new features that I have put into my application. And unfortunately, the mapping of my applications to physical hardware occurs at hardware purchase time, not at every sprint. So as my applications evolve, they evolve their way off of existing hardware platforms and potentially require new hardware platforms to support them going forward. So it functionally invalidates your purchase that you made last month. The mapping onto physical hardware also means that I'm not going to buy a single system for a single application because of the high core counts in my CPUs and the larger memory capabilities of our servers today. I am now going to layer, just as I do containers, I'm going to layer multiple applications on top of a single server, which means that I have to understand the complex interactions between all of the applications and their resource usage and potential contention and competition for those resources, so that when I build these systems, that they can support the load that I'm planning on. And that really forces IT managers to be really quite gifted system designers. They not only have to understand their application use cases and resource utilization from an application standpoint, but they also have to understand what the hardware is capable of doing and where the contention points are going to be, so that they can predict those. And it really is a specialized skill to really understand how to do that kind of design. And unfortunately, we compensate for that, not being able to do that adequately by over-provisioning. And this is one of the fundamental problems that we have today, is that because I don't really fully understand the interactions between my apps and their requirements and their contention, I compensate by putting, 40% more memory in the system, or 30% more cores to compensate for that. And that forces me to lose control over the cost model of my data center. I can no longer right-size my hardware for my load because my load constantly changes, and the servers themselves are fixed in time and space at purchase time. So that's the fundamental problem that we need to solve, and I think the multi-core server, that hardened single PCB that forms our server, is becoming the problem, that it is no longer the unit of app allocation. It's just too big and too complicated to use that methodology going forward. So that enters in the notion of what is composable infrastructure then. How does composable infrastructure solve that problem? And to start off with, the name implies that I want to be able to compose my infrastructure, kind of dynamically. Just as I, with containers, can pull together an app from pieces and compose it into a single container and then schedule it somewhere, I'd like to be able to do the same thing with my server. I shouldn't have to be dictated by designing that magical PCB that I then deploy. I should be able to do this dynamically through software. So I want to be able to compose my infrastructure from underlying pieces and parts. So how do I do that? Well, this is, the kind of the revolutionary piece of this is that this is the time to disaggregate that server board, to be able to actually break up compute away from memory, away from networking components, away from the accelerators, and have them separated from each other and not physically soldered together in one unit. And this is enabled by relatively newer technology that's been showing up in the last 5 years of high-speed, low-latency fabrics that allow me to interconnect essentially components in a server via a fabric and separate these things physically from each other. There are a number of these technologies that have shown up. We're not going to go into really any details about them, but this is the enabling technology that's happening right now, is that these fabrics are becoming as fast as the fastest buses that are currently in servers today. I mean, you can see fabrics that are approaching the speeds of DDR inside the server today. So that enabling a technology allows me to create pools of resources. No longer do I have to have one server with its dedicated resources. I can create pools of SoCs or pools of GPUs, pools of memory, and that allows me for horizontal scaling. That is, as the needs for more and more systems become inevitable as you move forward in time, you can essentially add to these pools and grow these pools over time to allow for more capacity and more capabilities horizontally. We then want to be able to, with software, decompose and compose systems when we need them. So if we have an application or a set of applications that need particular resources such as a TPU and certain memory sizes and certain persistent memory, we should be able to, just as we do with containers, have software APIs that drive the creation of virtual servers that create relationships between the components and allow them to communicate through these fabrics to accomplish the goals of the old server. The orchestration is really now being driven by my dynamic app requirements. That original problem that I was discussing earlier, that as my applications suddenly need more CPU resources, I can add additional processors. Or if they have additional memory requirements, I can add additional memory. So that's the fundamental idea behind composable infrastructure. And of course, this picture is a very simplified version of it. There are places where there are latency concerns and other things of that nature where you won't separate components. Like there will be essentially CPUs with local memory, but there will be other classes of memory that you'll use that'll have different characteristics of latency, but you will have greater capacity that'll be available out on the fabrics. So just take this as being a figurative example of what this might look like. And here's a little bit more detailed of a view of it, a little bigger picture for you. So if I had a application A and it required a system that had some GPUs in it, as well as some memory, a network interface card, and SSDs to support it, for example, like a machine learning application, I could read my data in across the network fabric to my SSDs into the memory, and then I can utilize my GPUs to access that memory to do some of the machine learning processes. But I essentially, using software, create a system by creating the relationships between the various components. One more physical look at it. Here are some of the fabrics that are available or that are being researched and used right now, which is, for a high-speed interconnect between my GPU accelerator and memory, I could use Gen Z, for example, to interconnect my CPU, GPU, and memory. I could use CXL, which is the next version of PCIe that has memory coherence built into it, to connect up to my PCI devices that are on a fabric. and then I could have an SSD that's speaking NVMe over fabrics, specifically in this example TCP, and allows me to communicate directly with those devices from in this system. So again, this is just sort of an example with some actual technology names in there about how I might assemble a system. So before I leave composable infrastructure, I thought I would also look at the storage component of it. If you remember, I was showing that a task has system requirements, but it also has storage requirements. And we have functionally been doing composable storage now for a while, utilizing software-defined storage methodologies. We have already created, disaggregated, scalable, composable storage. I can take a tier of servers that are connected directly to storage and essentially functionally create a virtual large pool of storage, and then allow my clients with API-driven mechanisms to allocate from that storage. So if, again, back to my machine learning example, if I needed to allocate a large volume to house my machine learning data, I simply use the APIs to say, give me, 10 terabytes of storage because I need to store this large data set for my machine learning application. And one of the things that we've seen, first of all, that whole mechanism is all automated and autonomous and driven by the application itself and the application requirements. So it is a composable infrastructure. But it has begun to show some of the issues with composability that we're going to see when we move into composability for the system itself. And that's, as we add fabrics between our devices and our resources, such as storage in this case, we do add a certain amount of latency, but usually the latency is offset with the functionality, increased functionality and flexibility, availability, and a bunch of other characteristics that make it worth adding that extra latency. But it also begins to consume more and more bandwidth on our servers itself, because we're now transferring data across fabrics, which means that we're utilizing internal DDR buses and fabrics to move this data back and forth. And in this particular case, you see this happening in multiple systems along the chain of storage delivery, which means that it's going to increase the need for power. Your fabrics require power to move things. You're going to have a larger bandwidth between your components, and it increases the provisioning costs. So the takeaway from this slide is that moving data in a composable world is almost the enemy, because it creates more cost and offsets the benefits of the flexibility and availability that composability brings to you. So finding solutions that help you with minimizing large data transfers between components becomes a very interesting problem to solve. And with that, I think we could stop here and see if there are any questions or anything before we move on.
Thanks, Philip. I've actually got one, but I think you partly answered it about where we are currently with storage and composable infrastructures, and you talked about containerization. So presumably you're referring to things like Kubernetes.
Correct.
Okay. What's the state of play?
So in the composable storage world, like I said, this actually is being deployed today all over the place. There's with Kubernetes, there is a standard called the Composable Storage Interface, which completely automates, from a container's point of view, how it acquires storage. It allows it to dictate exactly how much storage, what are the qualities of that storage that I need, and then be able to, with indirection, contact the storage layer and say, this is what I need, and get it allocated from the correct location from your storage pools that are underneath of you. And this is, again, this is back to the application requirements. Only the application knows exactly what they need. What are their latency requirements, what are their throughputs and capacities. And so by specifying this in the container storage interface, it allows it to dynamically grab its volume, and when it's done with it, it can return it back to the pool, so it can compose and decompose volumes on the fly.
Okay, thank you. Actually, just to point out to the audience, we've got a set of Kubernetes introduction seminars, there's 3 of them, in fact, that we ran a couple of months back, but I'll post the link up in the audience announcement area very shortly. The other thing I'd like to thank you for, by the way, is suggesting that Amdahl's law helps us parallelize applications. I thought, or rather, shows us the limits of parallelizing applications. I thought that was quite a good slip of the tongue. Anyway,
there's one more.
Actually, we may have a question from the audience as relevant to this.
Yeah.
Right. It's just a really brief question. A little confused about how moving data across an NVMe over Fabrics interface consumes DDR bandwidth. Can you elaborate?
Yeah, absolutely. So if you look inside of a server, a NIC card that is going to provide you with the NVMe over Fabric, whether it's RDMA or TCP, or even if you're using fiber channel, you'd have a fiber channel card sitting on a PCIe bus. The primary way it moves data across that bus is by taking that data from either memory and DMAing it to the device so that the device can then put it on the physical wire. So every time I move data in or out of a server through a network, there is a corresponding DMA that's occurring. And if you think about that, even for an SSD that's locally attached, an NVMe SSD that's even locally attached, it would really only take a handful of SSDs, less than 10, that can completely saturate a DDR bus with the amount of throughput that modern enterprise SSDs are able to do. So that actually is one of the primary bottlenecks that we're seeing right now, is that memory buses, especially for large data set problems. Let's say I'm doing, and you're going to see this at the end, we're going to talk about an actual example of this, but when you're having to move large data sets in for various processing, you literally can be bottlenecked behind your DDR bus and have to put more and more processors in to get more DDR bandwidth by parallelizing your application to leverage multiple processors and doing DMAs to different memory locations and leveraging the different buses to get an aggregate much higher bandwidth. DDR bandwidth is actually a big issue in our high throughput, low latency world that we're moving into.
Okay, thank you. Good, thanks very much. That was very educational, Philip. So I'm going to hand over now to Ellie Tiomkin. Ellie, take it away. What is computational storage?
Thanks, Alex. So computational storage as a concept has been around for a long time. However, we've seen in the last few years that it really gained momentum and started capturing attention in the storage world. And SNIA as an organization has adopted the concept and opened a technical working group and a special interest group to promote computational storage and to make sure that it falls under the same standard, so it will be easy to use within the ecosystem. So I will try and give a bit background on computational storage and then tie it all together with composable storage. Let me move the slide. All right. So when we look at the infrastructure of compute today, where we have a CPU, a memory, and storage, and as data sets become larger and larger, the problem of moving the data from the storage to the host for computation has created bottlenecks and problems. And the pain points are around, you can always deal with that by adding more infrastructure, but then there's always the physical space, the real estate location, the power, and the actual cost of putting a system that will meet the application needs. And that's what computational storage is here to solve. If we look at what computational storage does, then you take the actual compute function and move it to the storage. The compute sends a request to the drive. The drive process the request and return only the results. And the outcome is a massive reduction in data movement, because now you don't need to move the entire data set in order to run an application or container or execute anything, but you can do it on the storage, and you can do it in parallel. So take advantage of parallelism and distributed processing. And you can use it to do simple or traditional storage functions such as compression, decompression, encryption. And also you can run completely non-storage functions such as running databases, running AI, machine learning, dealing with images and videos, and doing all of that in the storage and not in the host. Now, the idea here is not to replace the host CPU or GPU, not at all. Computational storage is here to enhance, to augment the capability of the CPU without changing the infrastructure. So very easy programming model. You don't change your existing infrastructure of storage, and you enhance the total system efficiency in performance, reducing the power that the system consumes. SNIA had defined 3 different classes of computational storage devices, and I'm going to walk you through them. The first one is the computational storage drive, the CSD. This is one unit of storage device. It can be a hard disk drive or solid state drive. Now can have the compute inside the storage. The other class of computational storage devices is the CSP, the computational storage processor. So now you have a processor card that sits on the fabric, the same fabric of the storage, and accelerate the storage performance. And the third class of computational storage devices is the CSA, the computational storage array. Here you have an array of storage, which can be a hard disk drive array, an all-flash array, or a combination of both. And you have the CSA accelerating the storage on that array. So using computational storage allows the system to offload the CPU, and the CPU now can take care of other applications that require heavy-duty processing. Or from a system perspective, you can use a lower-grade CPU to increase efficiency. It really depends on what type of application that you're running. The benefit of computational storage, the main benefit is reduction in data movement. And today, nobody is really measuring the pain of moving the data because it's a default. You have an application, the application is running on the host or container. You want to run it, you need to move the data to the host. And as data becomes bigger and bigger and bigger, that's where the problems begin. And that's where computational storage alleviates the pain of power movement, increase performance, reduce power consumption of the system, and improve total cost of ownership. So the question is, are composable infrastructure and computational storage mutually exclusive or mutually beneficial? And I'll start answering that by saying that a composable infrastructure has been around much longer. So it is a much more mature technology that's been existing in the market. Numerous vendors provide numerous solutions, and it's being deployed all over the place. Computational storage is relatively a newer technology. However, it can fit in straight into composable infrastructure. Instead of using standard HDDs or SSDs or an array, now you use computational storage devices, and you take advantage of that within the composable infrastructure infrastructure. So I have one example, and this is example from a technical paper that it's actually about to be published at the ACM journal. And the problem statement is the ability to find the needles in a haystack. So we have an AI use case and computational storage devices. The data itself is images. And you have a large pool of images, and the data set is growing, and you see here the line of 10 million images in 2007 going to 1 billion in 2017 into a projected trillion in 2021. So massive increase in the data set. And now you're looking for a creative way of dealing with inferencing a new image that is that has to be compared to the existing data set. So an image has a vector that describes what's in the image. When you're trying to find the nearest neighbor or image similarity search in an AI type of application, what you're doing is you're taking that vector and you actually compare it to the entire data set vectors and trying to find the closest vectors and then find the results. That action requires you to scan the entire data set. And as the data set gets bigger and bigger, then your problem becomes more difficult to solve. Here is an example where computational storage had been applied, and the result is here we have a graph that describes only the host doing the loading time and the search time. So it's 40.5 seconds and 34.3 seconds to load the data set and search the data set. And again, because the data set is big, then loading has to be in chunks. You can't load the entire data set into memory. Now you have a system with 8 computational storage devices and a system with 12. And as we can see, the actual loading time had gone down dramatically, and the actual search time, linearly, as you add more drives, you get better results. So in terms of performance, we see a time reduction in loading time of about 95%, and time reduction in search decreased by 60%. So the performance of the system now with computational storage is much better. And usually, when you increase price, you have to pay a power penalty. And here we see the reverse effect. So not only that we increase the performance significantly, we're able to reduce the power by 60%. And the reason why it can be done is because of the reduction in data movement. Moving the data from the storage to the host requires power. And now that you have the host and 8 drives and or 24 drives are doing the same type of crunching, you don't need to move as much data back and forth from the storage to the host. Philip mentioned before that moving data is the new enemy of composable infrastructure. And I think that computational storage may be the solution to that problem, and adding computational storage with composable infrastructure architecture can be a double win on reducing the data movement in the system. And I believe that's what I have. Alex?
Thank you very much. Actually, there's a couple of questions. Ellie, I'm going to ask you the first one from the audience. How does computational storage differ from HCI or hyperconverged infrastructure?
So the computational storage, the application is now running inside the storage and in parallel. So you have the host that is running the application or container, and in parallel you have a system that is completely scaling up. The more devices that you add, the more compute that you have, like a bunch of minions that are now helping your host running the same type of application. So computational storage, it will be much more efficient in dealing with the large data sets and moving the compute to the storage.
Okay, that's a good answer. I've got one for Philip as well, which I think came from the previous section about the emergence of common buses. The question is, so the emergence of a single common bus between all the infrastructure components like CPU, GPU, TPU, FPGA, RAM, etc., will satisfy the needs of both composable infrastructure and computational storage? I mean, is this disaggregation the reverse of computational storage, or is it something? And I'm thinking in terms of the buses that we're using. Is this some way of, if you like, providing us with computational storage at a higher level?
Yeah, well, first of all, I would say that right now the reality is that there's not a common emergence of a single bus. There are different fabrics that are currently being utilized or thought to be utilized for different purposes, and it still remains to be seen how this will all shake out. You know, if I have the need for a high-speed memory coherent bus between peripherals, you know, CXL from, you know, the PCIe spec, you know, looks like it's going to be able to satisfy those requirements. But if I have the need for physically separating components by a greater distance than, you know, what's measured inside of a rack or inside of a, you know, inside of a single container in a rack, then I might have to be looking at Gen Z to get more physical disparity between the components. But of course, that adds latency and other issues as well. So right now, I don't think that there is a common bus that's going to interconnect all the pieces. And if you notice in my example, I actually showed the system that I generated utilizing multiple bus and fabric technologies to interconnect those pools. You know, using NVMe over fabrics for the storage looks like the most common approach that's going to be used going forward. But it could also be just vanilla TCP for storage devices as well. To that end, we see computational storage being looked at by, you know, not only by SNIA for how to define, you know, the APIs and how you would interoperate with a computational storage device across one of these fabrics, but I think we also see NVMe beginning to look at it as well. You know, going forward, I think you're going to see the incorporation of computational storage into our I/O protocols themselves to facilitate the use of it in a more holistic way, right? I think that, again, that the idea of separating on fabrics in a composable fashion for storage is an idea that we like and the people are utilizing today, and I think it's going to only grow as NVMe over fabrics continues to be deployed. And the next step is to find out ways to minimize, you know, wholesale transfers of data sets if we can, and that may mean that the application is running in the storage device, or it may mean just portions of the application are running in the device itself. I think these are all sort of interconnected, and I think they're all sort of complementary to each other.
Okay, thank you. We've had a couple of other questions as well, but what we're going to do is wrap this up and answer those questions on the blog. There is one I want to take before we leave today, and that's because it's a history lesson, and I'm probably the oldest person on this webcast, and I can remember some of this stuff. So somebody says, wow, this architecture is called a channel, and it makes me think of Amdahl. When in fact, it makes me think of IBM if you mention channels. Yeah. But what it really reminds me of is ICL, a famous British company in the 1960s and 70s that developed something called the Content Addressable File Store. You can find an entry on Wikipedia if you're interested. CAFS, as it was colloquially known, was used by British Telecom to do its directory inquiries. So when you phoned up to find out a telephone number, this is the days when people had telephone numbers that you actually had to look up. You didn't store them on your phone. You could ring directory inquiries, and they would use the names and possibly the addresses and use CAFS, which is very like a computational storage device. You actually fired the query at the disk drive, and it sent back the answers. So, hey, that was 50 years ago, would you believe? So a little history lesson there. But anyway, listen, thank you very much to you both to Philip and to Ely, for helping us get through this presentation, for presenting on composable infrastructures and computational storage. And thank you to you for watching our webcast. As you leave today, if you could rate the webcast, I'd be immensely grateful. And also, I'm showing here a couple of links. Probably the most important one here is the educational library. There you can find the references that I was pointing you to for the Kubernetes presentation. I'm going to put that link directly into the chat here. Just let me get the thing right. I'm not very good at old web addresses. There we go. So that will take you to the educational library directly. And we'll also post up the answers to the many questions that we've now had. I'm sorry, we really don't have time to answer all of them. But we will answer them on the website. And if you want to find out more about composable infrastructure and computational storage, then come to the SNIA.org/CMSI website, and you'll find a great deal of information on the work that we're doing here and the kind of technologies we're looking at and the kind of solutions we're proposing to develop over the next few years. But again, thank you very much, Philip. Thank you very much, Ali. And I would like to thank our audience for being a terrific audience, asking a huge number of really interesting questions. Remember to give us feedback on the way out. And wherever you are, enjoy the rest of your day. Thank you very much.
Thank you.